Hi, this is Satvik Rao from Group 8. Our topic is data discretization. Basically, these are the topics covered in our group PPT. In this video, I'm going to cover about introduction to data discretization. Data discretization is a way of turning a large number of data values into smaller ones, making data interpretation and management easier. Basically, it is a process through which we can transform continuous variables, models, or functions into a discrete form. We do this by creating a set of continuous intervals or bins that go across the range of our desired variable, model, or function. Like in simple words, we can say it is a method of transforming a continuous data attribute value into a finite set of intervals with minimum or no data loss. Various forms of data discretization. There are mainly two forms of data discretization. One is supervised and another one is unsupervised. Supervised discretization refers to a method in which the class data is used. In unsupervised discretization, it refers to a method depending upon the way in which the operation proceeds. It means it works on the top-down splitting strategy and bottom-up merging strategy. The main difference is supervised filters consider the class value while unsupervised filters doesn't consider. For example, the unsupervised filter only considers the attribute being discretized. While it can optimize the number of bins, it does so only with respect to self-encoding. However, the supervised filter will break the attribute into bins that provide the most information about the class. Let us consider a small example. Here, the age is a continuous data attribute consisting of many values. After discretization, it was transformed into multiple small intervals with no loss of data. Why it is used? This particular data mining technique enables organizations to obtain knowledge-based data. This enables organizations to make lucrative modifications in operations and in production. Comparing to other statistical data applications, data mining is the most cost efficient. It helps the decision-making process of an organization. Due to infinite degrees of freedom, continuous functions have a lower probability of correlating with the target variable and can have a complexly nonlinear interaction. Therefore, the understanding of such a function could be more complicated. Groups corresponding to the target may be viewed after discretizing a variable. Like as we discretize a model, we fit into bins and reduce the influence of minor data fluctuations. Sometimes minor variations are known as noise. By discretization, we will reduce this noise. Like this is smoothing method in which fluctuations are smoothed from each bin, thereby reducing the noise in the results. It also facilitates the automatic discovery of hidden patterns as well as the prediction of trends and behaviors. It can be induced in the new system as well as in the existing platforms. Like it is a versatile model. It is a quick process that makes it easy for new users to analyze enormous amounts of data in short time. It is also used in like it also improves the performance of machine learning algorithms. These are the various uses of data discretization. Thank you.
From Group 8. Today I'm going to tell the steps of involved in the data discretization and the types of data discretization. So, firstly, there are the steps involved in the discretization of binding, histogram analysis, entropy-based discretization, interval merging by chi-square analysis, cluster analysis, and discretization by integer partitioning. So, next to the types of data discretization. So, firstly, before that, the data discretization can be classified into two types, which is supervised and unsupervised. So, based on the supervised and unsupervised, we came up with the famous discretization techniques, which is histogram analysis, binding, cluster analysis, data discretization using decision tree analysis, data discretization using correlation analysis. So let's now see a one-liner or a brief about each technique. So first is the histogram analysis. Histogram is a graph that depicts a continuous data sets underlying frequency distribution. The histogram is useful for data distribution inspection, outliers, skewness representation, normal distribution representation. So from this, the after the analysis is done, so we get a result in which the data is data discretized values. So next is the binding. Binding is a data smoothing technique for grouping a large number of continuous values into smaller ones. This technique can be utilized for data discretization and formation of idea hierarchy. So and the binding is also a same little bit similar to the histogram analysis, in which once the end result is the data discretized result. So these are the types of data discretization techniques. Next is the cluster analysis. Data discretized is a type of cluster analysis to isolate a computational feature of a variable. Maybe let's take a variable x. A clustering algorithm divides the values of x numbers into clusters. Then next is the data discretization using decision tree analysis. A top-down slicing technique is employed in the decision tree analysis called data discretization. It is carried out under the supervision of medical professional in the numeric attribute discretization. You must first choose the attribute with the lowest entropy and then you must run it using the recursive process. Using the same splitting criterion, the recursive procedure divides into the discretized disjoint intervals from the top to bottom. Next is data discretization using correlation analysis. Here, the best surrounding interval in which the larger intervals are joined to produce a large overlap, resulting in which final 20 overlapping intervals. This technique is kind of overseen. And next is the generation concept hierarchy for nominal data. Concept hierarchy transforms the data into many layers. By adding partial or absolute ordering between the attributes, the definition hierarchy can be generated, and this can be achieved at the level of schema. Next is the entropy based discretization, an effective technique in handling continuous attributes for data mining, especially for classification problems. Next is the data discretization and concept hierarchy generation. The term hierarchy represents organizational structure or mapping in which the items are ranked according to the levels of importance. In other words, we can say that the hierarchy refers to the sequence of mapping a set of more general complex concepts to the complex concepts. For example, if you take a case of computer science, there are different types of hierarchical systems. So, if we consider a document is placed in a folder in the Windows at a specific place in the tree structure. Uh, Tree structure, then there is a specific place in the tree structure. It is the best example of the computer hierarchical tree model. So there are two types of the mapping. One is the top-down mapping and bottom-up mapping. So here, if you consider the top-down mapping, uh, begins as the name suggests, it's like basic information at the top and then concludes with the specialized information at the bottom. The bottom-up mapping often begins at the bottom and with the specialized data and finishes at the top with more generalized data. Thank you.
This is Hanisha. I am from Group 8 and I am going to explain about the top-down mapping and bottom-up mapping and also about the histogram analysis. And coming to the top-down mapping, in the top-down mapping, discretization starts with a single interval. In the top-down mapping will be done by using a single interval, and in the each step, one boundary is chosen. The number of intervals is incremented by 1 so as to maximize the quality of Q of A of the discretized attribute A, and the process is repeated until the quality of Q of A of a discretized attribute stops increasing, and the time complexity of the top down approach in the worst case is also of O n of 2, And however, since the number of intervals k is typically k less than n, the time complexity is usually in the range of O k of n. And here the each step is chosen with the maximum quality of the discretization attributes, and the time complexity will be O n of 2, and when there are k intervals, then the time complexity will be O k of n. And coming to the next line, I will be explaining about the bottom-up mapping. In the bottom-up mapping, the discretization starts with as many intervals as they are learning examples, and subsequently, the two adjacent intervals most similar with respect to the class probability distributions are joined. The process is repeated until the quality of Q of A of the discretized attribution A stops increasing. It will be repeated till the A stops in the attributes, whatever the attribute we have taken. Here we have taken the attribute A. It stops increasing. The process will be repeated, or there are only two intervals left. The time complexity of this bottom-up approach is O n of 2, and n being the number of learning examples. This is about the top-down mapping and about the bottom-up mapping. Here the time complexity is O n, n of 2. And coming to the next slide, I will be explaining about the histogram analysis. Histogram analysis. The histogram analysis is a graphical representation that divides a set of data points into ranges defined by the user. The histogram analysis is a graphical representation. In the right side, you can see the histogram diagram, histogram of multimodal. In the x-axis, we can see the multimodal, and in the y-axis, we can see the frequency. And here, in this graphical representation, the data points are divided by the ranges. Here you can see it is from 0 to 37.5, and then 45 and 52.5. It was defined by the user, and the frequencies are with the 5 intervals: 0 to 5, 5 into 5 to 10, and 10 to 15. And the histogram, which resembles a bar graph in representation, the histogram will look like an bar graph condensing a data series into a easily understandable visual by many grouping data points into logical ranges or bins. Here the histogram will look like a data graph, and the series, whatever happening in the histogram, will be easily understandable whenever the person was having a look at it. And these lines, which we can see also see in the bar graph, these are called as an logical ranges or bins. And coming to the next slide about the histogram. Continuation of a histogram analysis. Histogram analysis is an unsupervised discretization technique because it is unsupervised technique because it does not use the class information. It has no class information. Various partition rules can be used to define the histogram. In an equal width histogram, the values are partitioned into equal sized partitions or ranges. The ranges or the bins, we can also call this as bins, they will be equally divided with the equal frequency histogram. The values are partitions, so the ideally each partitions contain the same number of data tuples. They are equally divided, so the idea for having them into equally partitions is to have the same number of data tuples. And the histogram analysis in the data discretization, how it is done, and by using the what functions it has been done. For the histogram analysis in the data discretization, we can see in the coming next slide. To perform the data discretization by histogram analysis, we use this function which is called as hist function. His function that computes a histogram of given data values, and the function will provide the number of arguments. By using this his function, we can perform the data discretization. Data discretization can be performed. Thank you very much, and the coming slides will be explained.
Hi, my name is Shubham, and I'm going to discuss about cluster analysis. So cluster analysis is a statistical method for processing data. It works by organizing items into groups or clusters on the basis of how closely associated they are. The objective of the cluster analysis is to find similar groups of subject where the similarity between each pair of the subjects mean some global measures over the whole set of characteristics. Also, cluster analysis is an unsupervised learning algorithm, means that you like one actually don't know how many clusters exist beforehand, or like before they like we run the model, unlike like many statistical methods. Also, and cluster analysis is typically used when there is like no assumptions made about their likely relationships within the data provided, and it also provides information about where associations and the patterns in data exist, but not what those might be or what they actually mean within the like how what they are. And cluster analysis procedure can be viewed as like a pre-classification in the sense that the researchers or people who has not used prior judgment to the partition of the subjects. So however, it is assumed that like some of the objects are heterogeneous, that cluster exists. So that's the assumption. And this presumption of different groups is based on commonalities within the sets of inputs into the algorithm or clustering variables. And this assumption is different from one made in the case of discriminant analysis or automatic interaction detection, where the dependent variables is used to formally define groups of objects, and distinction is not made on the basis of profile resemblance in the data matrix itself. So there are various properties of clustering. To name some, like the clustering, scalability, high dimensionality, and so clustering scalability, this is a when there are like massive amounts of data and large databases needs to be dealt with, the clustering techniques should be scalable if it is to handle large databases, and the method should be able to handle both large and small data sets in high dimensional spaces. And also different kinds of data can be used with algorithms of clustering. It should be capable of like dealing with different types of data, like discrete, categorical or interval based data. And to deal with unstructured data, there would be some databases that contains like missing value, noisy, or errors in the data set. So if the algorithms are sensitive to such data, then it may lead to like poor quality of clustering or the analysis. So it should be able to handle the unstructured data given it data and give it some structure to the data by organizing it into a groups of similar data groups. And this makes the job of the people like easier in order to process the data and discover new patterns. And like coming to interoperability, the outcome of clustering should be like interpretable, comprehensive, and usable. So like that's what the main focus for using the clustering analysis is. And and to come to the various clustering algorithms, so there are like various clustering algorithms present. So for example, we there are clustering to name some, we have k-means, knn, expectation maximization, which is basically a Gaussian mixture model. And also we have like clustering algorithm named as like density-based spatial clustering of application with noise, which is basically called DBSCN CAN clustering, which we are going to discuss further.
K-means is a clustering algorithm where it calculates the centroids and then repeats the process until the best centroid is discovered. The number of clusters is presumed to be known. The clusters are randomly chosen in between the data points, and each data point is assigned to the nearest cluster based on the sum of squared distances. The flat clustering algorithm is another name for this algorithm. It is different from hierarchical clustering as it specifically tries to put the data into the number of clusters given. The letter K in the K-means denotes the number of clusters found from data by the approach. The data points are assigned to the clusters in this procedure in such a way that the sum of the square distances between them and the centroid is as little as feasible. If we add more clusters, the total variation within each cluster decreases. It is important to remember that less clusters diversity leads to more similar data points inside the same cluster. This clustering algorithm has its own advantages. Firstly, it is relatively simple to implement and identify unknown groups of data from complex data sets. The results are presented in an easy and simpler manner. Secondly, it is easily adapts to the new examples. K-means algorithm can easily adjust to the changes. If there are any problems, adjusting the cluster segment will allow changes to easily occur on the algorithm. It is very much efficient. The algorithm used is good at segmenting the large dataset. Its efficiency depends on the shape of the clusters. K-means works well in hyperspherical clusters. Also, the time complexity. The K-means segmentation is linear in the number of data objects, thus increasing the execution time. It doesn't take more time in classifying similar characteristics in data like hierarchical algorithms. The K nearest neighbors algorithm is a supervised classification algorithm. It is a super simpler way to classify data. It takes a bunch of labeled points and uses them to learn how to label other points. By using the data of labeled known points, this algorithm learns how to label other unknown points. In order to label new point, it looks at the number of nearest known points to the new point and then checks which label data has got more votes. So whichever label the most of the neighbors have is the label for the new point. Here K in K nearest neighbors is the number of neighbors it checks. It is supervised because you are trying to classify a point based on the known classification of other points. Based on the highest votes, the new point is labeled. This algorithm has its own advantages as well. Firstly, KNN is pretty intuitive and simple. The algorithm is very simple to understand and equally easy to implement. To classify the new data point, this algorithm reads through whole dataset to find out K nearest neighbors. Secondly, it has no assumptions. This algorithm is a non-parametric algorithm, which means there are assumptions to be met to implement the algorithm. Finally, this algorithm is versatile. It constantly evolves. The classifier immediately adapts as we collect new training data. It allows algorithm to respond quickly to the changes in the input during the real-time use. The Gaussian mixture models give us more flexibility than K-means. This model is a soft probabilistic clustering that allows us to describe the membership of points to set of clusters using the mixture of Gaussian densities. This is a less restrictive assumption than saying they are circular by using the mean. That way, we have two parameters to describe the shape of the clusters, the mean and the standard deviation. Taking an example in 2 dimensions, this means that the clusters can take any kind of elliptical shape. Say we have standard deviation in both the x and y directions. Thus, each Gaussian distribution is assigned to a single cluster. This model has its advantages. There are really two key advantages to using GMMs, which is the Gaussian mixture model. Firstly, GMMs are a lot more flexible in terms of cluster covariance than k-means algorithms. Due to the standard deviation parameter, the clusters can take on any ellipse shape rather than being restricted to circles. K-means is actually a special case of GMM in which each cluster's covariance along all dimensions approaches 0. Secondly, since GMMs use probabilities, they can have multiple clusters per data point. So if a data point is in the middle of two overlapping clusters, we can simply define its class by saying it belongs to X% to class 1 and Y% to class 2. That is, GMMs support mixed memberships.
Density-based spatial clustering of application with noise. This is a density-based clustering algorithm that works on the assumption that clusters are dense regions in space separated by regions of lower density. It has a high performance rate for a dataset where clusters have the constant density of data points. One of the significant attributes of this algorithm is noise cancellation. It groups densely grouped data points into a single cluster. It can identify clusters in large spatial datasets by looking at the local density of data points. The most exciting feature of this clustering algorithm is that it is robust to outliers. It does not require the number of clusters to be told beforehand, unlike k-means, where we have to specify the number of centroids. Binning discretization. In this method, the data is first sorted and then the sorted values are distributed into a number of buckets or bins. As binning methods consult the neighborhood of values, they perform local smoothing. This binning method can be used for discretization. It takes as input a set of continuous values, applies the discretization, and gives us output a set of discrete values. The attribute values can be discretized by applying equal width binning or equal frequency binning, and then replacing each bin value by the bin mean or median or by the boundaries, which is smoothing by bin means or bin medians or smoothing by bin boundaries respectively. Then the continuous values can be converted to a nominal or discretized value, which is the same as the value of the corresponding bin, which we will look at in the upcoming slides. Types of binning discretization: equal width or distance binning. This is the most common form of binning. It partitions the range of variables into k equal width intervals. The interval width is simply in the range a, b of the variables divided by k. It is given by the following formula. W equals b minus a the whole divided by k. Thus, the ith interval range will be given by the set of values a plus I minus 1 into w and a plus I into w, where I is a range of values varying from 1 to k. Skewed data cannot be handled well by this method. The second type is equal depth or frequency binning. In equal frequency binning, we divide the range a, b of variables into intervals that contain approximately equal number of points. This is a less commonly used form of binning. Each bin does not have equal width, but each bin does contain an equal amount of observations. Equal frequency may not be possible due to repeated values. Smoothing of data using binning discretization. There are three approaches to perform smoothing. The first one is by using bin means. In smoothing by bin means each value in a bin is replaced by the mean value of the bin. Mean is obtained by adding up all the values and then dividing that total number by the total number of values in the range. The second one is bin median. In this method, each bin value is replaced by its bin median value. The median value is obtained by taking the value lying at the midpoint of the frequency distribution. The third type is by using bin boundaries. In smoothing by bin boundaries, the minimum and maximum value in a given bin are identified as the bin boundaries. Each bin value is then replaced by the boundary value that it is closest to.
This is Venkatesh, and I am from Group 8. Our topic here is data discretization. This slide talks about data discretization using decision tree analysis. Discretizing with decision tree consists of using a decision tree to identify the optimal splitting points that would determine the bins here. Step 1. First, it trains a decision tree of limited depth. Using the variables we want to discretize to predict the target. In the step 2, the original variable values are then replaced by the probability returned by the tree. The probability is same for all the observations within a single bin, thus replacing by the probability is equivalent to grouping the observations within the cutoff decided by the decision tree. In the next slide, it talks about advantages for decision tree analysis. The decision tree written by the probability prediction is monotonically related to the target. The tree will automatically find the bin here. The next slide talks about data discretization using correlation analysis. It is a supervised approach. Discretizing data by linear regression techniques, you can get the best neighboring intervals, and then large intervals are combined to develop a larger overlap to form the final 20 overlapping intervals. The next slide talks about generation concept hierarchy for nominal data. The nominal data or nominal attribute is the one that has a finite number of unique values, and between the values there is no ordering. For example, job category, age category, geographic region, item category, etc. are the nominal attributes here. By adding a group of attributes, the nominal attributes form the definition hierarchy. It can create a definition hierarchy such as path, area, state, nation altogether. Concept hierarchy transforms the data into many layers. By adding partial or absolute ordering between the attributes, the definition hierarchy can be generated, and this can be achieved at the level of the schema. That's all, guys. Thank you.
Hello everyone, I'm Vineet. Today I'm going to present the discretization algorithm to find the semi-optimal set of cuts. This is the algorithm which we have implemented in our project. So to demonstrate the project and the algorithm, we have used the decision table as an example here. So in this example we can see we have the column A and column B having continuous values. So these are the two columns which we will be discretizing in this example, and D represents the decision attribute. So the first step of this algorithm is to basically list out all the domain values within the column, and then sort it out in an ascending order. So as we can see in example A, we have 0.8, 1, 1.3, 1.4 and 1.6. Similarly in B we have 0.5, 1, 2 and 3. So after sorting it in ascending order, we will basically generate the possible cuts between the values. So as we can see, the one cut would be from 0.8 to 1, 1 to 1.3, 1.3 to 1.4 and 1.4 to 1.6. Similarly for column B, we will have a cut from 0.5 to 1, 1 to 2 and 2 to 3. So now what we will do is we will take each and every row and then we will compare with all the other rows. So here we will basically only compare the rows which have the where the decision attribute is not same. So as we have here, right? So let's take an example of row 1 and row 2, so x1 and x2. So here, as we see, if we compare this both, we see that the decision attribute is not similar for the both of them. So we will continue the comparison, and we'll in order to write it this way, we'll basically check the range from 0.8 to 0.1. So over here we can see 0.8 to 1 is p1, so we will write p1. And then for the b we have 0.5 to 2, so 0.5 to 2 comes in q1 and q2, so we'll add q1 and q2. So now as we move from x1 and x2, x1 and x3, we see that the domain has 1 for both of them, so we will have to skip that one, and we will move to x1 and x4. So we will compare the domain. So okay, so domain is 1 and 0, so we can continue with this x1 and x4. So here we see the range is 0.8 to 1, which is p1, and we see the range for b is 1 to 2, so that is q2. So similarly we will compare each and every row with other rows, and we will get the uh, uh, all the formulas like this. So now once we get the formulas, we will basically create the table. So this is the table B. How this is generated is basically we write out uh, all the ranges. So it's p1, p2, p3, p4 for the A, and then q1 and q1, q2 and q3 for the B. And then so let's say in the, x1 and x2 we basically found p1, q1 and q2. So whichever values we have here, we'll add 1 for each and every uh, for each and every column, and similarly we will create the whole table. So now the next step is basically is to check whether to check which column has the highest amount of ones, and we will take that, and we will remove that column and all the columns which contains ones. So here in this example, all this column, all these rows will be also deleted along with this column. So after removing all the rows and columns, we end up with this table, and now we will further continue until and unless we have an empty data set, right? So here we see the column count for q2 is the highest, which is 2. So we will remove this column and all the rows which contains 1. So now we end up with only q3 and p4. So we take the q3 since it is the only column left now, and then we basically remove that. So now we end up with columns p2, q2 and q3. So here are the cuts for the p2, q2 and q3. So in order to create the optimal cuts, we basically take the range. So we take the average of 1 and 1.3, which is 1.1. So in our optimal cut, it would be from 0.8 to 1.1, and then 1.1 to 1.6. And for B, it would be we take the average of 1 and 2, which is 1.5, so it would be 0.5 to 1.5, and then again 1.5 to, we take the average of 2.2 and 3, which is 2.5, so it would be 1.5 to 2.5, and then 2.5 to 3. So after getting the optimal cuts, we basically replace the values for A and B according to the new optimal cuts which we get. So this is how we basically optimize, how we basically discretize the column A and B. Thank you.
I'll be discussing about the code for our project, which consists only of single file discrete.py. First of all, we import all the libraries which are required for running our code smoothly, ITA tools, math, CSV, pandas, etc. Um, the discretize class is used to function discretize the input data. The init function initializes all the member variables to null values or empty list. Then we have read function. Read function takes in path and uses the input file mentioned at the path and converts it into a data frame. And also it initializes the other member variables as empty list or null value. Then we have write function. Write function is used to store the transformed or discretized data after generating cuts and applying the semi-optimal method and storing it into a CSV file. Then we have transform function, which only uses two private functions, generate underscore cuts and transform underscore df. Then we have generate underscore cuts. In generate underscore cuts, the whole algorithm is being built. Then the first part is separating the attributes and the decision variable, then converting all the attribute from numerical or string into float, then taking out the labels from the decision column, 0 1 a or b as such, then finding out each label's indices and storing it into indices to pair, then pairing those indices based on the labels, since we are pairing the uh, rows who have different labels in their decision column. Then we generate cuts from each attribute. These cuts are generated using the average value of the unique values that we get from each attribute. Then we prepare rows and columns in a dictionary format, using each pair as key and empty set as value. Then this part of the code is is initializing is the step one of our semi-optimal cut algorithm, which initializes the whole initial table. Then this while loop consists of the next three steps, which is first finding out the optimal cut on the basis of maximum counts of the one, then deleting all the rows and that optimal cut uh, column from the table and finding out whether it is empty or not each time this happens here. Then we sort the cuts for each attribute in ascending order. We then use these cuts to transform the data into discretized form, that is converting the numerical variables into categorical variables for ease of building a machine learning model. So this part of the code is the code which actually runs and we get the input and output of the uh, in the terminal. Let's look at our output in the terminal. We first of all we are asked for input file location, then output file location, then it generates it shows us the data, generates the cuts for with the first, second, third number of cut. Then it also shows us the discretized data. Let's look at how our output file looks. So it is stored in the form of CSV file. So this discretized data is stored into a, CSV file which the user or we have mentioned. To summarize our whole presentation, first of all, data discretization makes the numerical attributes more compact and easy to build good models. And it is easy to build good models using such data. We also discussed about different types of data discretization, like histogram analysis, clustering analysis, etc. We also discussed about discernibility formula method and semi-optimal cut method, where we used semi-optimal cut method in our project, and we were successfully able to replicate this discretization method uh, in Python, which is actually similar to RSCS software that we saw in our lectures. Thank you. Have a good day.